Hello and welcome to the MOOC on optical communications. In this module, we will be talking about the bit error rate determination of that in optical on-off keying systems. So, this will after that we will review all the different methods that are available for on-off keying systems to detect the on-off keying systems and then move on to the higher order modulation techniques. So, let us begin by looking at what kind of model that we would like to consider in calculating the bit error rate of on-off keying systems. In one of the earlier modules, we have actually discussed BER of PIN receivers, APD receivers, receivers with coherent or the local oscillators or the coherent receivers, and receivers with optical preamplifiers, right. In each of these receivers, there are different noise processes which are involved and which dominate over all the other noise processes. We have quantified the operation of the system, the performance of the system by defining what is called as the Q factor, to which we have related the bit error rate of the system. However, we have not told you how to calculate those BER expressions, and it is instructive to do that for a simple on-off keying system because it brings out the difference between a simple wireless communication system which employs an on-off keying type of modulation versus an optical system that employs on-off keying modulation. We will see that the kind of assumptions that go into a wireless on-off keying system are slightly different from the assumptions that go into the on-off keying systems in optical domain. Okay. With that, let us look at what is the signal model that we are looking at. So, we have a certain data sequence, or in this particular case the data sequence is the same as the bit sequence. This bit sequence will be converted into a certain waveform, correct. This waveform conversion happens because you actually take a laser diode and then you take a external modulator, or you can directly modulate the laser diode itself, but in whatever way you do, you are going to generate these abstract bit sequences. Bit sequence could be 0, 1, 1, 0, 1, 1 and so on, right. These sequences are coming out every TB seconds, which means that this source is putting out these abstract bits, right. So, these are the bits, these abstract bits or the bit sequence at a rate of RB bits per second. So, this is the rate of the source which is generating the bits. However, these bits, as I said, cannot be directly transmitted over the optical fiber. In order to transmit them, you have to encode this bit information onto the amplitude or the power of the optical carrier. And if you take the power of the optical carrier and then switch between two levels, you are sending a certain optical power, say P1 when you want to transmit a bit 1, and you are sending an optical power of P0 which is usually taken to be 0. Later we will see that this will not be exactly equal to 0 for this case. Okay. For now we will assume that this is equal to 0. So, you encode bit 1 by transmitting an optical pulse. Okay. You can have various pulse shapes which we have discussed, but for now we are not even bothered with the pulse shape. Okay. We will assume that the pulse shape has been chosen and we have the receiver bandwidth that is sufficient in order to reproduce this pulse at the output. Of course, the pulse will not be exactly reproduced, there will be noise that comes along depending on what kind of receiver you are going to consider, right. So, with bit 1 represented as an optical power P1 and bit 0 represented as an optical power of P0, which is very close to 0, that we actually take it to be 0. This is then transmitted over the fiber. After transmission, we will assume that there is only one fiber link between the transmitter and the receiver. Okay. It comes to the receiver front end. At the receiver front end, you might actually have a band pass filter, an amplifier, or you can interchange the amplifier and the band pass filter because you need to first amplify the signal and then filter out the ASC components from that one. And after that, eventually you are going to have a photo detector, correct. So, this photo detector would produce a photo current. This photo current flows through a load voltage, and then this output across the load voltage would be the voltage that is generated corresponding to bit 1 and bit 0, and looking at this voltage and comparing it against a certain threshold, you are able to decide whether the bit is 1 or the bit is 0. So, this is essentially the link model that we are considering. For now, we will assume that this amplifier and the band pass filter combination that we have. So, this is the amplifier and the band pass filter combination does not really enter into picture. In fact, it is not required because the detection can be done, or the basics of the bit error rate can be established without reference to these, and the effect of having a gain and an optical band pass filter can be added later or can be discussed later. So, we will look at this model, okay, and what we are interested is this quantity called bit error rate. Okay. So, if you expand this, this stands for bit error rate, and this is a quantity that is normally found on commercial modems. Okay. So, you or on anything that you are going to purchase, or in system design where you are asked to keep the bit error rate to be less than 10 to the power minus 9. However, the word rate should tell you something else, right? Rate is something that is with respect to time. When a quantity changes with respect to time, that is the way it changes with respect to time is captured by this rate. However, when we quote BER, we normally say that this is 10 to the power minus 9, and this does not seem to be represented with respect to time. What we mean here is a normalized bit error rate, okay, normalized to whatever the bit rate that we have chosen. Okay. Although we do not specify the bit rate, this factor is actually normalized to RB. So, to obtain the bit error rate in seconds or per second quantity, you have to multiply the bit error rate that is normalized, which we can call as the probability of the bit error. That is, if you transmit a bit 1 or a bit 0, what is the probability that that bit will be incorrectly received at the receiver. So, you take that probability of error and multiply it with the bit rate in order to tell you how many bits you are making or how many bits are there in error. So, let us remove this E. So, how many bits are there in error per second? For example, in earlier 2.5 and 10 Gbps systems, the standard that was used, BER value that was used was anywhere between 10 to the power minus 9 to 10 to the power minus 12, with 10 to the power minus 12 more common for a 2.5 Gbps system and 10 to the power minus 9 for a 10 Gbps system. With this one as the bit probability of bit error, okay, what we have actually specified is the normalized bit error rate, which is actually the probability of the error. When you multiply this one either by say 2.5 or 10 Gbps, the kind of bit errors that you are making would turn out to be, so let us calculate this one for the 10 Gbps system. So, 10 into 10 to the power 9 bits per second is what you are actually transmitting. When you multiply this one with 10 to the power minus 9, this 10 to the power minus 9 will cancel 10 to the power 9, and what you get is you are making 10 bits, or in your received signal you have 10 bits in error at each second, okay, on an average. Of course, this is not exactly a science saying that, I mean this is not exactly saying that this is 10 bits will be in error, it is on an average 10 bits will be in error. Okay. When you have 10 to the power minus 12, then the errors that you are making per second will be even smaller, right. So, this would be 1 into 10 to the power 10, 10 and minus 12 is there, which would be 10 to the power minus 2, so which is 0.01 bits per second, correct. So, these are the typical values that you would have seen about 15 years ago or 10 years ago when you had a commercial 2.5 Gbps and 10 Gbps systems in operation. These values turn out to be very nice. However, in modern optical communication systems, we normally fix this probability of error or the normalized bit error rate to 10 to the power minus 3 to 10 to the power minus 4. Now, you might question, with 10 to the power minus 12 and 10 to the power minus 9, you are seeing bit errors of 0.01 bits per second and 10 bits per second. Wouldn't we have increased the number of bits in error by relaxing the requirement for probability of error? You would be right, we have relaxed the requirements of probability of error. However, there is another process called as forward error correction, which is supposed to take care of, okay, so this is forward error correction, which is supposed to take care of the extra gain or extra loss that we are experiencing, and applying the forward error correction, you can change the systems with an initial 10 to the power minus 3 or 10 to the power minus 4 probability of bit error into 10 to the power minus 9 or 10 to the power minus 12 bit error probability or probability of error. Okay. So, this process is actually accomplished by what is called as forward error correction, and therefore the FEC limit, FEC stands for forward error correction, this FEC limit is typically 10 to the power minus 3 and 10 to the power minus 4 in modern coherent optical communication systems. Okay, having established what BER is, let us actually look at how to calculate this probability of error. The bit rate of course is fixed by the system designer, there is no control of that one for us, but we would like to see what can we learn more about how to obtain the probability of error, and that is what we are going to do now. Okay. To obtain probability of error, we need to first understand what is exactly happening. Okay. When will we get an error? Suppose you have transmitted a certain optical power P1, okay, which stands for a bit 1. Once this propagates through the fiber, the power actually kind of reduces, obviously, right. The power at the receiver side would be P1R, and this power would be less than whatever the power that we have launched at the transmitter side because of the loss in the fiber. Of course, fiber also has dispersion, which means the pulse will spread out from its original time slot and interfere with the next pulse, but we will assume that those dispersions has been compensated and therefore we do not really worry about that. Okay. Please also note that this is a waveform with respect to time. Okay. So, here you have a pulse which is varying with respect to time, and let us assume that for all practical purposes is the same pulse, which is same pulse variation is maintained, except that the amplitude has now decreased. Okay. Again, this is something that is varying with respect to time. If I put in a photodetector here, what is that I am going to generate at the output? I will be generating the current waveform, okay, which looks very similar to the received optical waveform, okay, and it gets multiplied by this responsivity of the photodetector. So, you have a photodetector, the current waveform that you are generating, which will again be a function of time, okay, will be R times P1R. If this is what has happened, it would have been, life would have been very easy for us. We could have simply amplified this current and then did all our detection, later on. Unfortunately, we know that this photodiode is going to add some noise, correct. So, it is going to add some noise, okay, and this noise, in addition to the noise added by the photodiode short noise, because the current is supposed to flow into a certain load resistor, which we can take as the input impedance of the preamplifier or the amplifier, post amplifier as we call it. So, that post amplifier input impedance is RL, okay. There is a certain thermal noise associated with that RL as well. Okay. This thermal noise is of course independent of what optical power you have transmitted, it simply depends on what is the temperature at which the resistor has been kept, and this resistor or the equivalent temperature, and this resistor with the value of the resistance itself. Okay. So, this is the waveform that you have received, and if you have transmitted in the next slot a 0, you would also see some amount of noise. Now, compared to a typical radio receiver which you would find in any of your cell phones or in the older radios, the noise levels for bit 1 and bit 0 are different. In fact, the noise that you see, the variance, the noise variance of bit 1 is greater than the noise variance of bit 0. Can you guess why that is so? The answer is, bit 1 when you have transmitted, you have received a certain power P1R, and the current that you have generated is R into P1R. Okay. The average current that you have generated during this particular portion of the pulse would actually determine the short noise, and this is given by 2Q R P1R BE, where BE is the bandwidth that we have used. So, we are assuming that after this you are going to use a low pass filter whose bandwidth is BE, which we normally take it to be B by 2, where B is the bit rate. Okay. So, B is the bit rate, and we normally take that one to be equal to the bandwidth of the electrical filter to be equal to B by 2. Okay. The total noise when you have transmitted 1 actually is given by 2QR P1R BE, this is the short noise component, plus there is a thermal noise component. However, when you have transmitted bit 0, the only noise that you are going to get is thermal noise. Why? Because we have assumed that the received power when a bit 0 is transmitted is equal to 0. That is because we assumed that the transmit power when you are transmitting bit 0 itself is equal to 0. This was the transmit power, we had assumed that P0 is equal to 0. In case your laser is not able to make P0 is equal to 0, in addition to this there will be a short noise component that corresponds to how much power you have received when you have actually transmitted bit 0 flowing in the same bandwidth, okay, flowing in the same resistor and having the same bandwidth. Okay. However, in practice this term is very small. So, this is actually kind of very close to 0. Okay. If not, you can always include this particular thing as an extra noise. But what are these noise that we have been actually talking about? Well, if you go back to the link here, what happens is after you have this current waveform, you do not exactly use the waveform to detect. I mean, you do not use the entire waveform to detect. What you do is you sample the signal at its best sampling time. Okay. If it is a 1, you normally sample it at the middle of the bit period, so that where the eye is quite wide open. We will talk about eye diagrams in another module, and you again sample at the middle of the bit in order to obtain the next voltage or the current sample. Okay. We will assume that you are sampling the current, and therefore, this current which you have sampled at time Tk is given by Ik. Okay. This is a photo current, and the sample time at Tk plus 1 where you have sampled is given by Ik plus 1. Okay. Of course, at different time instances you are actually sampling the current, and it is this current that you are interested in. What would this current consist of? This current would consist of whatever the transmitted signal that you have. Let us call the transmitted signal at the time k as Sk, plus there would be noise component Nk. Okay. So, this is the signal plus noise that you are looking at. Now, is an interesting question. What would be Sk? Sk would be R P1R when bit 1 is transmitted, and we will continue to assume that P0R is 0. Therefore, this would be 0 when bit 0 is transmitted or when bit 0 is received. Okay. Now, this noise unfortunately is not something that can be pinned down at the beginning of the transmission. So, noise is actually what we call as a random variable. Okay. Noise is a random variable because predicting its exact value is not possible. You can only talk about the statistical properties. It is like taking a coin, okay, and tossing it. So, if I take a coin and toss it, right, then beforehand I will not be knowing what would I receive, what would the coin be there on my palm, whether I would have a head or a tail received on the coin. I will not be able to know that. Okay. Or if I take this pen and I throw, right, there is no guarantee that I will always catch this pen at the correct stage. Maybe I would catch, but maybe I will not catch. I can only talk about the probability of catching or the probability of the head showing up or the probability that the noise voltage at the point where we have sampled across a load resistor RL is greater than 3.3 volts or it is less than minus 1.1 volt, okay, or the noise current would be less than 2.3 amperes. So, I can only talk about the probabilities of these events, and of course, I can talk about on an average what happens. On an average, what is the value of the noise voltage across a load resistor. If it is a white thermal noise, Gaussian distributed noise, then on an average it would be 0, that is the voltage if you average out the positive and the negative values times where you get the positive voltage and negative time voltages. In the long run the average voltage will be 0, but there will be a variance associated with that, there is a variation or a fluctuation associated with that. So, we can determine what is the fluctuation of the noise process. Okay. So, you can learn more about all these random variables in any of the other courses, or you can refer to this chapter on probability and random processes in this book called Digital Communications by Simon Hyken. Okay. So, if you look at this book, it gives you a nice idea of what probability is, what random variables are, and how these random variables are distributed. For us, noise is a random variable, and as I said, this noise variable Nk is usually modeled as a 0 mean, which is on an average the voltage of the noise is 0, but it has a certain variance sigma. Okay. This variance for when you transmit bit 1 will be sigma 1 square, when you transmit bit 0 this would be sigma 0 square. Usually sigma 1 square is larger than sigma 0 square. Now, this kind of a behavior is not at all seen for a radio receiver. In the radio receiver the noise will be 0 mean, which is perfectly fine, but whether you transmit bit 0 or bit 1, the variance will always be the same. So, the variance will be equal to each other for a radio receiver. Okay. However, for an optical receiver, these values are not equal, right. So, these values are not equal for an optical system. That is because the noise sigma 1 square, the noise variance is different from sigma 0 square. Sigma 0 square is the noise variance when you have transmitted bit 0, and that noise just includes a thermal noise, whereas sigma 1 includes both thermal as well as the short noise component. So, the variance itself depends on the input that you have transmitted, and if you sketch the probability density function of this noise process. So, let us say there are this the noise process corresponding to bit 0 and the noise process corresponding to bit 1. Okay. F of n0 is basically the noise process when I have transmitted bit 0, and then f of n1 is the noise process when I have transmitted bit 1. And if you look at these processes or the probability density functions, you will see that the corresponding probability density function, we are assuming it to be Gaussian. So, if you look at a Gaussian function, this is the noise that you are obtaining, or the noise probability density function when you have transmitted bit 0. It would be situated at 0 and it will have a certain variance of sigma 0 square. Whereas, the probability density function when you have transmitted bit 1 will be situated at a mean, or it would have a mean value of r p1r. Why is this so? Go back to Sk. Sk is equal to p1r, r p1r when you have transmitted bit 1. So, the received current Ik will be given by r p1r plus the noise component. And what is the average value of this Ik, which is obtained by operating this expectation on this one? Since this is a deterministic quantity, so this would be just r1 p1r, okay, plus the expectation or the mean value of the noise voltage, but this is exactly equal to 0. However, the variance of this noise process Ik when you have transmitted bit 1, okay, is given by sigma 1 square. Therefore, the noise process corresponding to this one will be different, and it actually has a variance that goes something like this. Okay. So, this have actually different heights simply because sigma 0 square is less, therefore, its variance should be smaller, but the area under this curve f of n0 or f of n1 should be equal to 1. Okay. Now, coming back to what is this PE, PE is the thing that happens when you receive a bit and decide the bit in the favor of 1, but when the actual bit that was transmitted was 0, right. So, you commit an error whenever you erroneously decode the bit or determine the bit. So, this PE can be written as what is the probability that I am going to decide 1 when actually the bit 0 was transmitted, and what is the probability that 0 itself is transmitted, plus what is the probability that the receiver or I will decide the bit as 0, but when we have actually transmitted bit 1 times what is the probability that you have actually transmitted 1 itself. Okay. So, these are known as conditional probabilities, and these are the conditional probability errors, and multiplying them by P of 0 and P of 1 removes this preconditioning. If you are not catching this particular point, you can refer back to the ASC noise derivation. There we had the photocurrent given certain optical power was received, and then we removed that preconditioning thing, right. So, we removed that conditioning thing, and that is what you get over here. Normally, you assume that you are transmitting zeros and ones equally, that is on the long run these probabilities are equal to half. So, you are left only to calculate what is probability of 1 given 0 was transmitted and probability of 0 when you have actually transmitted 1. Okay. So, let us actually consider first this case, probability that the receiver thinks of this as 1 while the transmitter has sent a 0. Okay. When you have sent a 0, right, what would be the received current after sampling? So, the current corresponding to bit 0, right, if you have transmitted bit 0, you should at the kth sampling time, the current that you are going to see Ik0 will be equal to S0 plus N0, where S0 is actually equal to 0, because S0 is nothing but R P0R, but we have not transmitted any power, so this would be equal to 0. So, when you sample the current waveform when bit 0 is transmitted, at that particular time you are only sampling the noise voltage, and that noise voltage we have called it as N0. This would be 0 mean, right, and it has a certain probability density function which we have assumed to be Gaussian, which means that the probability density function of the noise current of n0 is given by 2 pi sigma 0 square or 1 by root of 2 pi sigma 0 square e to the power minus n0 square by 2 sigma 0 square. Okay. This is what we have plotted in this graph. So, this f of n0 is the probability density function that we have plotted. Okay. When will I make an error? Suppose I have received this one. Okay. When will I make an error? Well, as I said, I am going to put up a threshold, correct? So, I will put a threshold and I will subject this particular voltage that I have received when I have transmitted bit 0 to the threshold. In case this IK0 happens to be greater than the threshold, okay, the current threshold, when this happens I would have declared this as a bit 1, and that happens when this current sample becomes greater than the threshold current that I have set. However, IK0 is nothing but N0 because S0 is actually equal to 0. Therefore, this probability can be rephrased in terms of the noise. Whenever you sample the voltage or sample the current, if the noise in that current when the bit 0 is transmitted becomes higher than the threshold current, right, if the noise is so strong that it actually moves up the sample value beyond the threshold, then there will be an error, right. So, the probability that you are actually declaring a bit as 1 when you have transmitted 0 is just the probability that the noise would be greater than the threshold, okay. And this can be easily obtained. Why? Because I know what is this probability. If I take a probability density function that looks like this, okay, as a function of say some independent variable x, so this would be f of x, the probability that an event lies between say x1 and x2 is given by integrating the probability density function from x1 to x2, okay, of this f of x dx. Similarly, if I want to know what is the probability that noise is greater than ITH, I am looking at the probability that of this entire area. So, the probability that is there within this entire area is simply the probability that the value x is greater than x1, okay. The probability that your output is greater than x1 is obtained by integrating this x1 and moving this x2 to infinity, okay. So, you can simply write down what you are going to get here. This would be the probability that noise is greater than the threshold current, okay. So, this is actually given by ITH to infinity, that is the noise current will be greater than the threshold current. There is a 1 by 2 pi sigma 0 square over here which I forgot to put in, and then you have e to the power minus n0 square by 2 sigma 0 square dn0, okay. N0 of course you recognize is just a dummy variable. I could have written x here and nothing would have actually changed over here. I can relate this probability, okay, or this expression to what is called as the Q function. The Q function is defined as Q of x is given by square root of 1 by 2 pi integral from x to infinity e to the power minus some dummy variable this fellow, okay. So, this particular Q function is simply telling you the probability that for a 0 mean unit variance random variable, this has to be a 0 mean unit variance random variable, what is the probability that random variable will take on a value that is greater than or equal to x, and that is what the Q function will tell you. So, you can rearrange this one, we are going to talk about that in the next module, okay, and complete the expression for the probability of error. Thank you.